Welcome everyone for Cloud Computing and Big Data. Today we have our lecture 3. And after quite some time of having now spent with, an invited lecture with Andreas Lintermann last week, covering actually a lot of fundamental concepts in machine learning, in parallel and distributed computing, which in one way or another is all related to your industry projects, especially when you think about transformer models and the more cutting edge, let's say, AI that was covered. It's time for us to also come back a little bit to the lecture series. And don't worry, the industry project is very important for us. So that's why we spend a lot of time having lectures on agile project management with Ingolfur, but also now with Andreas, some, let's say, a glance of lots of different methods that you may use in your industry project. So for cloud computing itself, today we will basically continue what we had in lecture 2 and now looking a bit more what Apache Spark can do for cloud applications, which brings us to pipelines and etc., etc. But before we dive into the material of today, let us review what we had then the last time in our lecture 2. And lecture 2 was really about machine learning fundamentals. So we started this a little bit with having an overview of machine learning, if you remember, where you can all algorithms in a way put in a bucket, and most of them, which are best understood, are supervised learning classification models these days. But there's also clustering. If you don't know classes yet, you can do some similarity measures in order to find out where are classes or potential groups of data. And then there's sort of real-valued regression tasks where you can have certain trends analysis and so on. But another fundamental aspect, if you remember, was always the 3 ingredients for a machine learning problem, which is basically that you have a feeling for a pattern, right? So a pattern must exist. If there's no pattern, there's nothing to look for in the data. If you remember, machine learning means learning from data and learning patterns from data. So then the second point would be if there's already an exact mathematical formula, there's in a way not really a point of learning from data again, because this mathematical formula that solves your problem might be straightforward to implement, use it, done. So it's also no reasoning in a way for doing machine learning necessarily. And then the third one, it's really something you can't live without. And this is definitively data exists because we're learning from data. So this was basically the fundamentals, and also today in lecture 3 we will cover more and more fundamentals. We'll also give you a little bit an overview where the different elements of machine learning sit that we use along these lines that we just discussed. And what we then had was essentially the simplest machine learning problem that you can have, a binary classification problem. And then we had also a very simple learning model, perhaps also one of the simplest learning models you can have, which is the perceptron learning model. And the idea was here to mimic a little bit a very, let's say, easy way of a neuron, really, to have, different signals in our data set X with different attributes. And then the supervised mode gives us a class here, basically Y, where we can learn from. And the idea is then to learn these red weights, right, that you have up. So you sum them up linearly using weights, these inputs, and add a bias. And then you have your first signal that's going through. And you can always determine if that's correct or not by looking at this Y. And if you remember, for mathematical convenience, we have put the same that we see here using the sign function for, binary classification, +1, -1. And then essentially what we see here, basically the input data, the attributes summed up linearly using weights, and basically putting the bias in that we also can then learn with, this WI. For mathematical convenience, we have here the vector notation W transpose X. So there's also nothing very special. So it's just a little bit, if you remember from your mathematical basics. However, intuitively, what we do with these W's and changing them, and this brings us back to the hypothesis set, is, that we have different hypotheses, and these are characterized by these lines. So first, we have the hypothesis of saying it's a perceptron learning model, but how the weights are and how the weights will end are all very different. So these are all different hypotheses. And of course, we want to get the, decision space right of this blue and green colors. So what's actually happening with the perceptron learning algorithm, that I don't pick it here now, but was essentially shifting this W by adding and subtracting a vector through the space in order to get all the, let's say, items right. You see here the blue point misclassified. So the algorithm will shift and will work on the weights, as you have seen in lecture 2, until everything is correctly classified. And this is a goal, and this is also the limit of the perceptron learning algorithm in a way. So it has to be linearly separable. And also Andy last time in last week's was talking about this from the more practical perspective. Of course, linear separability is something which you not necessarily can assume in data. Hence, today we have much more sophisticated algorithm, but just not using one perceptron, but combining these different ideas of a neuron to neural networks, what we have seen last week. And we also will come back to this and then using that in clouds. Then, when we want to be a little bit more sophisticated, instead of the sign function, we have used binary classification with so-called logistic regression. So we put it through the logistic function, having then every signal that comes out is basically of the same idea that we had with a linear learning model here. So you see the dot product is nothing else, and you see here with W transpose X. But we bring it through the, through this logistic function, which means essentially that every value will be in a way squashed between 0 and 1 again. But we have a, let's say, more smoother path to it in this logistic regression model. We use some optimization. We will also come back today. And then from the application, you have seen this can be already quite different, although we have stayed in the realm of linear learning models. We had this binary classification. We started from basically from the classification of the flowers, Irisitosa, Irisvirginica, if you know what is a new flower about. And we want to know, and experts in machine learning, use then these algorithms to say, okay, this is a Irisitosa, Irisvirginica, and hardly any human can tell that. Hence, we go for machine learning, right, to help and support the humans. Maybe some experts in plants can tell you about this, sepal width and sepal length and so on. But usually that's the idea of using machine learning. And this was even more obvious if you said there are lots of, basically properties in humans, no matter what their profession, if they want to have a bank deposit or not, if they are savers or not. So this is something where also then humans basically have maybe some gut feeling about some persons, and I don't share which profession maybe would do that. But in the end, you would say that the machine learning can actually capture these different, let's say, properties or attributes of a person much better than maybe human, from education, marital status to job, et cetera, et cetera. So we worked on this a little bit also, if you remember, and the idea is also to do this a little bit in your assignment. But let us come now to lecture 3 today. If we continue basically along these lines with machine learning, but more and more we will add now cloud computing, cloud applications, because we're not a machine learning course alone. We want to blend this with computing needs, with storage needs, and I will make a big case for it, especially in lecture 3 when we start today, when we have real data science examples. And then you will quickly realize that some solution tools we gave you in the beginning of the course, like Google Colab, and some of you using this for the industry, they also have their limits, and we will explore that. And then we come quickly to the idea of using Apache Spark at scale. It's a data analytics framework that is really scalable with so-called worker nodes, and we will make a case for it, and we'll also basically then update our practical stepwise approach by using not Google Colab anymore as we had before, but using the MS Azure HD Insight, which is a cloud service, one of many. We will also explore in the remainder of the course AWS services, which are very similar, and also the Google services, which are also very similar. Then, of course, we take another idea of a new application, the food inspection, that we have here as an examples. And throughout the course in part 1 and part 2 today, the idea is that you get a better understanding also of the mathematical building blocks of machine learning. So where is the test set, where is the training set, where are the algorithms, where are the models, where is the computing? So all of these different mathematical building blocks will be more or less put in a systematic fashion in some of the slides so that you have a better understanding as well. Then we continue with this, of course, in the second part, where we then will move more and more to a systematic use of cloud computing. The industry wording for this is also often using, pipelines, where you essentially use the same pipeline that you use for training. So maybe, if you remember the CRISP-DM process we had, work on the data preparation, data understanding, then go back to data preparation. I don't need this attribute. So you form essentially a small part of a pipeline where you prepare the data for the machine learning. Then you have the machine learning as well, which algorithm, by now, there's not only the perceptron learning algorithm to pick or the perceptron learning model, there are a wide variety of AI models to choose from. And, the ones you choose is another part of the pipeline. Where do you compute? Another part of the pipeline. Which optimizer to use? Another part, etc., etc. So this is something where, this is in a way another approach of having a systematic way of doing machine learning. And in later lecture will be also more open and, we call them basically ML ops tools, which are also systematically working on this. But here is also the idea that you use the same pipeline that you use for training and testing, and we will make a case for it. And also we'll see how this is nicely supported with PySpark when you use cloud computing resources like HD Insight, but in a very similar way, it works also with AWS services in the cloud and also even Google Proc services. These will come in later lectures. So today we really focus on this one on HD Insight, also because it's related to your last assignment in a way, apart from the hackathon that you will soon also start. So fasten your seatbelt for, let's say, another way of seeing, machine learning, starting perhaps from one of the challenges, also understanding why machine learning these days needs cloud computing, why it needs high performance computing, which is usually also underneath cloud computing. So in lecture 2, we had already the Google Colab Cloud, which is sort of nice, and it has a Jupyter notebook interface, a very nice GUI, if you want, in the web browser. And we had this interesting, step where you can even have a subscription of this. But in the end, you have just one resource available. We come to that in a moment. We deploy a Spark cluster there in Google Colab. We have done that and use basically this Jupyter notebook-like interface really to code our Python code around the application problem that we have, which was in our case then perhaps the Iris Itosa, Iris Virginica idea or others. It doesn't matter. And then you have a Spark session. You would inspect your data set, loading it, running it, maybe perhaps even visualizing it to understanding better. And then you would perform machine learning remotely, right, on the Spark cluster. Now you will realize that the collaboratory is hardly a cluster, right? So all you can choose is a one GPU, and even that is not, let's say, deterministic, always the same one, and you cannot have more than one. And this is the idea of the course today, to make you feel a little bit what it really means to use cloud computing at scale. Google Colab is a good way of starting. It's a good way of being in a cloud already. It's very closely connected, of course, to the Google services and so on, but it's not at all, let's say, a scalable HD Insight server in Spark that we will explore today. So when we now look in some application problem, and some of you are actually involved in this. I mean, some of you do with our SME Greenfish, our partners in industry, for instance, one of them, the industry project. So when you use this Copernicus Marine data store, and also for the others to know that it's an open data set repository. So there are a wide variety of data sets available that people can use. And Copernicus is a large European, let's say, endeavor to really open up more data. And this is also, to speak, the foundation of the team behind SME Greenfish, right? They have different products. They're growing significantly. They're using high performance computing in a way with this, also the cloud computing resources. And they make use of this Copernicus Marine data store. For instance, as some of you know from the industry project, they use a global ocean sea surface temperature. And if you want to data access it, you have to register a little bit, but it's all free of charge, which of course helps SMEs today like Greenfish to really strive. And they combine not only the sea surface, of course, they have obvious much more data available, satellite image data, and use machine learning algorithms, all with this combined to enable a precise fishing forecast. So in one respect, reducing diesel fuel in this large ship fleets that are really fishing globally today. So it's a huge market, very interesting use of high performance computing for us. And for you, an obvious reason to understand a little bit more the quantities of data we talk with as one of the motivator, where are the limits of going away from Google Colab to others. Now, for some of your industry projects, it has been downscaled. But if you really want to do a production project, if you want to be, an SME, like SME Greenfish, you have to have the resources. And one best way to understand this is if you just pick maybe the data from the last 5 years, available as the global ocean sea surface temperature, which is important for the fishing use case, you suddenly end up with 370 gigabytes. Well, then good luck to just upload this in your Google Colab. I have here an example, just actually of 2.8 gigabytes, and this already took almost infinite time. So using this with a drag and drop idea with 370 gigabytes, not a good idea. There are APIs around that you can use. Some of you know that from the industry project with the Copernicus data, but then you also quickly have the trouble that actually you have maybe not enough gigabytes available anyway, right? On this Google Colab with 68 gigabytes. So 370 again, 68. There are some, basically subscription mechanisms that you can look in, where you maybe have a little bit more of storage, where you get better computing. But you can quickly realize when you do more data analysis, like things we do, for instance, also in the HPC course, like the wave propagation right on an ocean, and you want to have for initialization and for validation if your modeling is correct, all the sea surface waves and so on, you quickly end up with 5.8 terabyte. Repeat, terabyte of data. So there is really then where you 60 gigabytes or something, which is here remaining maybe in one of the Google Colabs I use, is quickly at the end. Even if you subscribe to more storage, you hardly get, basically quickly up to 5.8 terabytes. So hence, storage is a big problem here, right? So for real production problems, it's usually boiled down for early machine learning courses. It's good for small data analysis. But when you do really large runs, this is not an idea in terms of storage. But let us come to compute, which is equally limiting, right? You see here what happens if you change your runtime. And if you do the practicals, you will basically understand a bit more what this means. You can pick here between different types of GPUs, an A100 here and so on. While here it's even not anymore available. You have to subscribe to Colab Pro and pay the price for it. Starting already with the idea, of course, that cloud computing services cost, right? So this is something to realize. And of course, it starts even with a free Google Colab, which essentially, if you want to really use it for, let's say, cutting edge machine learning today, is not anymore free. You have to already pay Google Colab Pro. And even then, you get faster GPUs, let's say from a T4 generation GPU to an A100 NVIDIA card. This is not at all, what you need maybe in an application problem. You see here one examples of our satellite image analysis for land cover. We use different HPC resources where, basically we have this 24 nodes in jewels as an example here in the blue one to really get the time to solution really down. So we use 24 nodes, but each of the nodes has 4 GPUs. And then you have, let's say, 96 GPUs in parallel used to solve that problem. So good luck with Google Colab there. So in the end, it is a good tool, but this also motivates us to look at other solutions. So what happens if people have this demand, like we have seen in SME Greenfish, how you actually get along with having much more computing needs. And this is something what we want to explore a little bit today, and of course in the remainder of the course in general. So, and of course, for some of you that are interested much more in this larger scales or the waves that we discussed and so on, feel free to join us in the complementary HPC course, right? That will be coming again in spring next year for those of you that have this course not taken yet. But let us come then back to our stepwise approach we had in the cloud computing course. Now we update this a little bit using an interesting cloud service called MS Azure HD Insight. And obviously, this is already a paid service, so you also have to pay here. But the benefit is really you can scale up as many GPUs you need and using an interesting technology that we already know, Apache Spark at scale. The stepwise approach is very similar. So you still, need a subscription that's not relevant for your assignment because essentially we have done the subscription for you and you can just use a HD Insight cluster. But when you want to do it yourself, you have to have a subscription like pay per use, which is quite attractive. So you just really pay for the resources you use. But you have also the drawback to always, have to stop your cluster if you don't use it. You have to manage your cluster. Otherwise, you're running quickly into quite some cost. There's a deploying of the Spark cluster very similar, like we basically require to get to the PySpark kernel to really use the functionalities of Apache Spark and to create a Spark session and so on. Here we use some, specific resource manager template. And when you have then, the interface of this, used from HD Insight, you can again also get some Jupyter Notebook basically interface, which is, the similar one that you are familiar with Google Colab, and then start crafting your, let's say, Python application. And this goes the same way. And some of these scripts are even very portable, right? Meaning that when you have a Google Colab script, with some modification, you can maybe quickly get it also running in HD Insight. Because the steps that you do for data analysis, visualization, is Python, is also maybe parts already of the PySpark session, when you especially do the machine learning, as we will explore today, and then also the evaluation refinement. So this course of action that you to do there is hardly changed if you want to use HD Insight. So let us look a little bit now, what is this fantastic Apache Spark framework? So this is coming out of a more, let's say, data analytics idea that constantly data is growing, right? And you try to have decentralized data stores here and there all used in order to perform, machine learning, have a decentralized way instead of just high performance computing, one big cluster at some location, offering 5,000 GPUs. So here the idea of distributed computing was much more in. Actually have carved first something called Hadoop, which will come up in later lectures. For the sake of getting the assignment out earlier and not at the end of the course completely, we wanted to have this in memory processing with Apache Spark first, which is more or less also much more used perhaps today because it has really this benefit of optimizing many of the steps that you have inside the Spark execution for this in-memory task, like the MapReduce task and so on. So hence, this is a framework which stands the test of time. And you see here an example when you perform logistic regression with Hadoop versus Apache Spark. Spark is much more faster using this in-memory benefit. Now, when we now look essentially what does Apache Spark really enables, it's much larger as you think. So there's a huge ecosystem around the open source tools of Apache Spark, of Apache Hadoop, and many of the Apache projects and, those that are also doing, key value stores, like you have here Cassandra, for instance. Apache Airflow enables you workflows. Kubernetes, distributed basically deployment. We will talk about this, Kubernetes and even Kafka later on in the course, Mongo database. You see many of these players just for storage are very well working together with the Spark engine. And then Spark itself is really designed for doing data science at scale, has many machine learning algorithms which have a parallel execution inherited in the ML libs that you can use, because you cannot just use scikit-learn or other machine learning algorithms out of these toolboxes and throw them at a cluster to be parallelized. You need a parallel execution, you need a parallel algorithm to make that happening to really work in a distributed fashion. So how Spark is doing this is by having essentially the PySpark session, creating a Spark context, and then you have a cluster manager that you basically can choose from, like Hadoop Yarn is often used, leveraging those from Hadoop, enabling really a multi-use of this cluster. And the multi-use will come more in lecture 4 when we talk about data center design and multi-tenants, why different people at the same time use one cluster, and hence virtualization to the rescue. We will talk about this in lecture 4 more, but then also at scale in lecture 13 about Kubernetes, for instance. And the cluster managers will then schedule and control and operate with so-called worker nodes, right? And these worker nodes is now the inherent principle why this is all scalable. So you can add or remove worker nodes to your problem when you start a Spark application, and the whole framework is able to, work with much more worker nodes or less, depending on what you configure. And in this are the machine learning tasks and combined that you basically can stretch across different worker nodes, contributing to one big machine learning model. So this is something, which is, very often used. When you go to the Spark website, you will see it's also interoperable with many of the elements that you know maybe from other lectures like pandas, or basically even, SQL, structured query language for database access. Spark SQL is there. So it has really an idea of working distributed with things you already know. And of course, not all machine learning algorithms are parallelized here, right? So this is also another point. Some of them are parallelized through mechanisms you already know by PyTorch, maybe this deep learning packages, and so on and so on. MLflow is an MLOps package I was alluding to. And you go on and create basically the problem that you want in Python. For instance, it has different other languages, but it's really interoperable. And, as I said, in the cloud computing offerings, Apache Spark is essentially in all the big cloud vendors always present. We use MS Azure HD Insight for this. So hence, this lecture should be showing you a little bit how that works step by step. So we start with the first step saying, we need the subscription, and there are some aha effects I wanted to give you alongside. For instance, if you have a pay-as-you-go subscription, you go there, you basically need to register then which exact service you want to use. And this is an interesting insight that you have to configure first. So if you swipe the credit card in a way, have pay-as-you-go created, so you're registered in this, you still can't use the HD Insight per se directly. It takes some configuration if you want to do it. And you see here how that works. You basically have to create a HD Insight cluster, and before that, you really have to register essentially this resource provider and this HD Insight cluster, so being even able to create one. And this is an important aspect to really also make you realize this is very costly if you use this. So there's some way also for people to really understand when they do this that there could be massive costs, and that the registration makes you aware that now you're entering really a production service 24/7 available. But with this, of course, you have to be very careful because the costs can skyrocket. And the reasoning for this is that, of course, you are in a way now responsible to think how many of these worker nodes you need. So how scalable your application should be. So here's a good illustration how it works a little bit. Not all of that is obvious to you. We have to do this step by step in the course. Virtual machines, virtualization will come in lecture 4 a little bit. But if you have this kind of idea of in this MS Azure cloud, and there's someone, going with a web browser or via SSH to this cluster, you have the head nodes. These are the managers of, basically within Spark dealing with all the workload. And you have usually two, for, let's say, really operational issues. If one gets down, the other one can take over and so on. And then you have some zookeeper nodes, which essentially is another project from Apache, taking care about the distribution, taking care about, managing the whole cluster load, and particularly also your number of worker nodes. And you see that the zookeeper nodes are relatively free and don't need to be necessarily those which have a large, memory, because the more memory you want to use for it in these cores which are available, the more costly the estimated costs, right? Memory is very expensive, hence the cost per resource can quickly skyrocket. If you have just 4, it's 2.70 € as an example here, but this is per hour, right? And if you want to have for 1 month, 24/7, you do the math times 30 or something, then you basically have quickly costs that can skyrocket. And 4 worker nodes is not really a big cluster, right? Some have 20, some have 100, right? That use MS Apache Spark on a daily basis. So hence the costs can quickly accumulate. But of course, you get also then a very scalable solution, very quick answers then again, basically essentially for your machine learning problem. Hence, you see It's in your hands a little bit how big the cluster should be. And that brings us to the scalable cloud computing, right? In some occasions, you need a cluster maybe with 100 worker nodes at the end of the year where you want to process lots of data for maybe some text purposes, some builds, you want to accumulate machine learning, do some trends. But then, during the year, maybe in summer vacation, you want to boil down your cluster to a couple of resources, hence the cloud idea. Expanding, shrinking, right? The idea of a cloud. So you can really modify this by the number of worker nodes. Hence, I said the head node is relatively fixed with two, should not be one usually, and the zookeeper nodes. But the worker node enables, the flexibility of the whole cluster and about this HD Insight service. Now, the other end, when you think about that, in the end, one worker node is, of course, something which relates to power, GPUs, CPUs, something we discussed in terms of, computing power in the beginning of the course. There you can, of course, also change the different core types, right? They have all different price ratios. You can look on the website on HD Insight services, how many cores they have. But in order to leverage Spark, you would use something which has large quantities of, RAM. You see the Zookeeper node has here a very interesting resource which costs almost nothing because there's also nothing much RAM needed. It's more managing, node really. But if you go and make the math and see here 64 gigabyte per RAM and the even more powerful ones, you quickly come into, much more costs per hour. And then when you want to register these particular type of CPU, you also maybe don't have them directly available. Another thing that you see here as an example for you, just that you realize this, for some of them you have to even ask, right? So you have the quota also to protect you in a way, right? If you have the quota always unlimited and by accident you put 400 worker nodes, you quickly see that your manager runs in your office and would cry and say, well, what would you do here with the cost of the cloud? Are you crazy? So the quota also enables you a little bit to be very, let's say, precise about the amount of resources you needed and to prevent here and there accidents when people, have, let's say, mysterious wishes in terms of how many worker nodes or whatever they need. Hence, you have to ask about specific quota increases manually in order to get, let's say, in your subscription pay as you go, then, the computing resources you need. Hence, for people that use a Spark cluster, maybe some application domain experts and so on, this is already something where you go below, let's say, the level of detail that maybe they need to know. Hence, in application domains and so on, and in companies which are an application domain, like let's put Greenfish as an example, you have little one like Siggy, who's really a technical expert, right? While others may be more the fishing experts and do other things, usually it is good to have someone who knows a little bit more what's really behind it to understand the cost and to understand also lots of the technology you need and what is available. You see here, we can pick Spark, we can pick Hadoop, HBase. When you start a certain cluster type, you have to, use a subscription there, have a resource group, and all of that you will also explore a little bit when it comes to our assignment. So then it's a bit more easier to realize. But you use an existing resource group and an existing cluster in order to execute in the cloud something. And, then you can pick Spark for an example and, others if you want. Pick specific versions which have, specific properties. So another thing which goes a little bit more to technical detail. But once you basically agree on the resources, we discussed this already, and you see here the contribution is 54 of 78 available cores. We have asked for it, we get it. Then basically have a deployment in progress. This could actually take some time, a couple of minutes to be deployed. And once it's deployed in this time, then the money accumulates also for your costs. So be very careful if you use that within your own company or basically outside in a company where you're employed for. Make sure you have a very good overview of the costs. They're actually good cost explorers that enables you to understand better this, accumulating costs. Also remember, and this is a very important takeaway message, although now the Google Colab, you have actually started this, then have the Jupyter Notebook environment very conveniently, don't care much about costs. Here, the cluster is running. if you use Jupyter or not, right? So hence, the Jupyter is just the interface to the cluster, which you can then use using the PySpark kernel here in this Jupyter that you can quickly and nicely actually connect with your executed Spark cluster. But the message is if you essentially close Jupyter, the cluster is still running. And with this cluster still running, the money is still accumulating. Hence, this is a bit disconnected from the Google Colab experience you have, right? So the cluster is running all the time. Some people may use a Jupyter notebook. The application experts don't have to care about the cluster at all. They just click on Jupyter, get their application interface, run it in the cloud. And, we will see some examples later. But this is something which you really need to be aware of. I mean, you and your assignment in this course, you don't have to, right? We have created the cluster for you, the deployment and so on, and the cost is not for you. But essentially, when you come to a company and you're running this 24/7 and it's never used, it's also cost that you don't need. And with this, it's also, get the message out there for you, very important. Always think of maybe shut down the Spark cluster. That is possible without destroying it in a way. So you can basically also stop the cluster, then the resources are not used anymore, but can be reactivated with the same, configuration and so on. And this is an important part to really get into your head from the practical experience, especially if you grow with a number of nodes. With your worker nodes, be careful, be mindful of the costs. So motivating a little bit our application problem that we want to analyze a little bit. We want to have an advanced application example. This time we use something called binary classification of see if they really will pass or fail with a food inspection of some restaurants that we already discussed briefly before. We go along the line of CRISP-DM, but this time in lecture 3, we also want to systematically create this medical building blocks, right? So we don't overdo it with going back again to CRISP all the time. I will make some connections, but by now, also do the industry project that, you should model a little bit along these lines you learned already with CRISP-DM. We put an emphasis rather on the mathematical building blocks, but of course, the whole idea is following roughly the CRISP-DM model. So what we have here is lots of text data from the food inspection from the city of Chicago as an example here. This is also available for you online, the original data. And, sort of the violations then of the food kitchen quality of, being, clean, non-clean and so on. All of this will give us maybe an indicator if the overall judgment is that basically the restaurant should be closed and basically the food inspection failed. So this is an interesting use case, bringing us to the supervised learning example. So there's already lots of data available that we have, the training examples, if you remember. And luckily, someone has already labeled this, giving us the opportunity to learn from existing cases if the food inspection failed or not. So we will learn on this, making it the training examples, right? So the attributes you have here for each individual restaurant. And then we know the outcome, and we have all the restaurants and all the data essentially here. So we want to find out some essentially target function in a way that really created this, but the target function we will never know, right? If we would know it, we would just hit and implement it to get the next food inspection right. So hence machine learning starts from this kind of data that we have, examples that we have. So let's put that in our systematic overview, which is now really a practical machine learning overview for you at hand to see and understand a little bit where the different building blocks are. So there was, in some way or another, some ideal function that was creating these training examples that, we will never know exactly. And we don't need to know. That's the beauty of it. And we will create here much more mathematical building blocks to get the machine learning right today. So we start with these training examples, right? As I said earlier, connected to the things. Without data, there's no machine learning, right? So this is really something you must have. And of course, here are the big demands for storage. You have seen the Copernicus marine data, right? Quickly going to terabytes of data. So this is our first formalism. And we build on this throughout, the lecture 2 part, or lecture 3, the second part of it. So given the time, we will stop here, make a break. Also to understand a bit more the runtime architecture of Spark applications, here was a YouTube video for you to look, and then we continue with the second part of the course after 5 minutes break. So see you then.